Welcome back to Linear Algebra for Economists. In this video, we will revisit systems of linear equations and see how one might apply the concepts of matrices and determinants to solve systems of linear equations. First, let's talk about market equilibrium. When you combine the supply and demand curves of a given product, there is a point where they intersect. This point is called the market equilibrium. The price at this intersection is the equilibrium price, and the quantity is the equilibrium quantity. At the equilibrium price, there is no shortage or surplus. To find the equilibrium price and the equilibrium quantity, we need to solve the equation supply equals demand. For example, let's suppose that we have a supply and demand function of a product given by these two equations. Now in this case, market equilibrium would occur where the supply is equal to the demand, that is, negative 600 plus 200p equals 1200 minus 100p. Solving this linear equation gives us that the equilibrium price is p equals 6 units, and plugging this value back into either s of p or d of p would give us what the equilibrium quantity is. Now, if s or d is a nonlinear function, then we would have had to solve a nonlinear equation here. We will later see that calculus provides us tools that enable us to approximate solutions of nonlinear equations by solving linear equations. So this way, in a sense, solving linear equations is sufficient. And if the supply or demand function depends on more than one variable, for example, not only the price or not only the price of this one product, we might have multiple variables. And likewise, if we are looking for the equilibrium for many products, we have many equations to solve simultaneously. That is, we are going to have to solve a system of linear equations in that case. Now suppose that we have two competing products, A and B, and both of their supply and demand functions depend on both of their prices, as seen here, in whatever convenient units. Now market equilibrium would occur when supply equals demand for both of these products. In other words, we have two linear equations to solve simultaneously. In this case, the solution would be P1 equals 49.2 and P2 equals 64.8 units. Substituting these prices back into the equations would give us positive equilibrium quantities, so both products would actually participate in the equilibrium and neither one is outcompeted by the other. So we can hopefully see that it's worth knowing at least something about systems of linear equations if someone wants to be an economist. Now let's recap the usual methods of solving systems of linear equations that one might have learned about in high school. First, we have the graphical method, which we can use in the case of two variables and two equations. One upside of this method is that it's visually obvious because we need to visually find the intersection point of two curves. Downsides of this method include that it's only useful for two or maximum three variables, otherwise we would need to be able to see in multiple dimensions, and that's already difficult in three. This method is only useful when this solution is sufficiently nice, so just looking at the intersection point we can read their coordinates. And finally, this is very difficult to automatize, so it's very difficult to write a code that would automatically find the graphical solution of systems of linear equations. Now the second method that you might have learned about is the substitution method. So in this method, one makes one of the variables the subject of one of the equations and then subsequently substitutes it into all of the equations, thus reducing the number of equations and number of variables by one. So if we keep going systematically like this, eventually we'll be left with a single equation for one single variable which we could solve. One upside of this method is that it's algebraically obvious. This is useful for 2 to 4 variables, otherwise for a larger number of variables this becomes difficult to algebraically deal with. This is also useful when the solution is not very nice, but the calculations therefore might be ugly. And this is also somewhat difficult to automatize, though not as difficult as the graphical method would be. And for a third method, we have the method of elimination by equal coefficients. We will see a bunch of examples for this method shortly. This one is somewhat algebraically obvious and also useful for any number of variables. The calculations won't be much worse than the substitution method. The biggest pro of this method is that it's very easy to automatize. Now let's take a look at some examples of this method of elimination by equal coefficients. So let's suppose that we have the system of linear equations 2x plus y equals 11 and 3x minus y equals 9. Now notice that if we add these two equations together, the plus y from the first equation will cancel with the minus y from the second equation, thus giving us 5x equals 20, from which we can conclude that x must have been 4. And substituting x equals 4 back into the first equation, we can conclude that y equals 3. For another example, let's consider the system of linear equations 2x plus 5y equals 25 and 4x plus 3y equals 15. Now, there are no equal coefficients in this case, but if we multiply the first equation by 2, we will have 4x plus 10y equals 50, in which case we do have equal coefficients, and from now on we can proceed as before. We could also choose to multiply both equations by some number, so in this case we multiply the first equation by 3 and multiply the second equation by 5, thus giving us 15y in both equations. And now, subtracting the first equation from the second one, we would have eliminated y's from the equation. Note at this point that it's not really useful to store or write down these x's and y's and equal signs, so we can just write down the numbers that we are dealing with at this point. So that would of course lend itself to the use of matrices very nicely. And to solve these systems of linear equations with the help of matrices, we can have two strategies. In the first strategy, which we will learn about in this video, we can just store the numbers in matrices. And another approach would be to utilize matrix multiplications to solve the system of linear equations. This we will look at later down the line. So in this example, we have to solve the system of linear equations 3x plus 5y equals 21 and negative 6x plus 7y equals 9. We can rewrite the system of linear equations as the augmented coefficient matrix, as seen here. And we can do the same operations as we have done before, now with the rows of the matrix. So first, we multiply the first row of this augmented coefficient matrix by 2, giving us 6, 10, and 42 in the first row. And therefore, we have equal coefficients in the first column. So if we add the first row to the second row, we will have eliminated this negative 6. After doing that, the second row is 0, 17, 51, which lends itself to a division by 17, and therefore we can conclude that y must equal to 3. And at this point, we can also eliminate the 10 above the 1 by subtracting 10 times the second equation from the first one. And finally, dividing the first row by 6 gives us that the solution is x equals 2, y equals 3. In the next example, let's solve the system of linear equations 3x plus 12y equals 21 and 2x plus 8y equals 14. Again, we can rewrite this system of linear equations as just the augmented coefficient matrix. And here we can divide the first row by 3 and we can divide the second row by 2, giving us 1, 4, 7, 1, 4, 7 in both rows. Notice that both of these rows contain the same information, or in other words, I could say that we subtract the first row from the second one, leaving us with a full 0 row in the second row. This would mean that we have only one equation. The second equation doesn't add any new information to the system, meaning that we would have infinitely many solutions in this case. So both of these equations that we started with would be equivalent to x plus 4y equals 7. So we can specify either x or y to be whatever we want and therefore calculate what the other variable would be. In our next example, we can divide the first row by 3 and divide the second row by 2, giving us the rows 1, 4, 7 and 1, 4, 9. And these would be contradictory rows, because if we subtract the first row from the second one, we would get a 0, 0, 2 row, which would correspond to the equation 0 times x plus 0 times y equals 2. And there are no such real numbers that would satisfy this equation. Now, based on the last few examples, let's notice that a 2 by 2 system of linear equations has a unique solution if and only if the coefficient matrix, in other words, this 3, 12, 2, 8 in this case, so not the augmented, but the coefficient matrix, has a non-zero determinant. Otherwise, there could either be infinitely many solutions or no solutions at all. So notice that in this case, the determinant would be 3 times 8 minus 2 times 12, which would of course be 24 minus 24, which is 0, in which case here no solutions exist, and here with the same coefficient matrix we had an infinite number of solutions. Whereas in the first example, the determinant of the coefficient matrix would be 3 times 7 minus 5 times negative 6, which would of course not be 0 because we are adding two positive numbers together, and in this case we had a unique solution. Now we can have more than just two equations to deal with, so in this case we have a system of linear equations with three unknown variables. Now notice that in here x1, x2 and x3 are in different orders in each of these equations. So if we write down this coefficient matrix, we would end up with this one here. And here we can divide the first row by 4, divide the second row by -9, and leave the third row unchanged, which would give us that two of these rows are actually redundant, so we can get rid of them. So at the end of the day, all three of these equations were equivalent to 3x plus 2y minus 5z equals 0. So we could freely choose any two of these variables arbitrarily and then calculate the third one. Next, let's take a look at this system of linear equations. Again, the order of x1, x2, and x3 are all over the place, so when we write down the augmented coefficient matrix, we need to take care of that. Here, after dividing the first row by 4, the second row by 8, and then the third row by 6, we would end up with the following augmented coefficient matrix. The second row is a copy of the first one, so we can get rid of that. And we can also subtract the first row from the third one and divide by -8 afterwards, which would give us that the third unknown, x3, or here I wrote z, must be equal to 0. And then the first row indicates that 2x plus 3y, or if you like 2x1 plus 3x2 must be equal to 1. So z is not a free variable, it has to be 0, but one of the other two variables could be a free variable, so we could choose x1 or x2 to be whatever we want. Now let's collect what we have been doing in the last few examples. So these row operations constitute something called the Gauss-Jordan algorithm for solving systems of linear equations. So we had a bunch of steps allowed, which are basically the same steps as we would allow for the method of equal coefficients for linear equations. So we can multiply or divide any row by a non-zero number. We can add or subtract one row from the other. If we have a full zero row or a duplicate of one of the already existing rows, we can delete those, and we can change the orders of these rows however we want. And the goal is to get the left-hand side of the augmented coefficient matrix into what we call a reduced row echelon form. Let's take a look at some of these coefficient matrices in reduced row echelon form. So this is formalized here. If there is a row where every entry is 0, then this row lies below any other row that contains a non-zero entry. The leftmost non-zero entry of a row is equal to 1. The leftmost non-zero entry of a row is only non-zero entry in its column. And if we have two non-zero entries, they are located in this stepwise situation. So let's now take a look at another example. So let's say that after some elimination steps, we are left with this augmented coefficient matrix. What can we get from this? So from the third row, we can deduce that x5 must be equal to 12 over 3, which is 4. So we can rewrite the last row as a bunch of zeros and then 1 and then 4. And then as the next step, we can use this 1 as a pivot element and reduce all the numbers above it to be 0. So add the last row to the first one 3 times and then subtract the third row from the second row 2 times, which would leave us with this coefficient matrix. Now notice that we cannot get rid of x3 and x4 in either of these equations, so in either of these first two equations. So they must be free variables. They can be whatever they want to be, or whatever we want them to be. So we're going to say that x3 is some parameter c and x4 is some parameter d, while we also concluded that x5 must be 4. For the rest of the scheme, we will move this c's and d's to the right-hand side of the equation. So from this matrix, we would get this augmented coefficient matrix. Notice that in the first row we had 3x3 in the beginning, and having moved it to the other side of the equality sign, it will appear with a negative sign. And therefore we can go on with our elimination steps. So dividing the second row by 2 would give us this row. And then using that 1 as a pivot element and subtracting 3 times the second row from the first row, we get rid of that 3 as well, leaving us with the coefficient matrix on the bottom left. And finally, we can divide the first row by 2, giving us a 1, 0, 0, 1 on the left-hand side, and a bunch of numbers on the right-hand side. Now let's take a look at what this means for our solutions. So just reading off what row 1 says. Row 1 says that x1, so 1 times x1, is equal to 9 plus 0 times c, which we don't write down, plus 1 times d. And the second row says that 1 times x2 is equal to negative 4 minus 1c plus 1d, which we can see here in the middle. We've named x3 to be c and x4 to be d, which are arbitrary parameters, and then x5 had to have been 4. This is what the solution of a system of linear equations would generally look like. We have a bunch of parameters, and we may have variables that are not free to be whatever they want to be. So note that this solution may also be written in what is called a parametric vector equations, since two vectors are equal to each other if and only if all of their components are equal to each other. This enables us to get the following geometric intuition for this solution set. This is actually a 2D plane floating around somewhere in 4-dimensional hyperspace. The blue part would describe the span of two vectors, which is a plane that includes the origin, and that this plane is shifted by this red vector. So this would look something like this, only in 5-dimensional space, which is somewhat difficult to draw on a slide. Now I want to introduce two more concepts that are useful when we talk about solution sets of systems of linear equations. So first we have the subspace, which is that the subspace of an n-dimensional Euclidean space, or N, are lines, planes, hyperplanes, and so on that include the origin. So this is not a rigorous mathematical definition, but this is how we like to think about this geometrically. So with formulas, this is what this would look like. So these are possible linear combinations of a bunch of vectors. In our previous example, we had 2 vectors. And the other concept is an affine subspace or vector space, which is just a shifted version of this subspace. So this does not necessarily include the origin, this one from before. And solutions of systems of linear equations are always some affine subspaces of the input space. Of course, if solutions exist. Now finally, let's introduce a rule that utilizes determinants to find the solution of a system of linear equations. So, as I mentioned before with the 2x2 examples, an n by n system of linear equations has a unique solution if and only if the coefficient matrix has non-zero determinant. So let's suppose that we have A, which is an n by n square matrix with a non-zero determinant. We have an arbitrary vector B, and we're looking to solve the matrix equation AX equals B, which is equivalent to a system of linear equations. In that case, we can get the jth unknown variable, so the jth coordinate of the solution vector, as the fraction of 2 determinants. So in the denominator, we have the determinant of the original matrix, which of course has to be non-zero. And on the top, we have replaced the jth column with B and compute the determinant that way. Please note that calculating both determinants is usually very time-consuming. So Cramer's rule is more of a theoretical tool that we like to use. Let's take a look at 2 examples of this. This is a system of linear equations that we have already solved in the beginning. So X would be the determinant of this modified matrix divided by the determinant of the original coefficient matrix, which gives us 2. And likewise, Y would be the determinant of this modified matrix divided by the determinant of the original coefficient matrix. In this case, that would give us 3. In the next video, I will show you how one might implement all of what we've learned about so far in a Python coding environment. See you there.